Now in this lecture we will look into preparation of aryl halides and arylalkyl halides. Now first let's look into what is an aryl halide. Aryl halides are compounds where the halogen atom is directly attached to benzene ring, right? You can see this halogen atom is directly attached to benzene ring, right? This is named as chlorobenzene, right? And your aryl alkyl halides are compounds like these, right, where halogen atom is attached to the side chain, right? You can see this is a side chain, and this is named as benzyl chloride, or you can also name it as chlorophenyl methane, right? This is chloro, this is your phenyl, and this is the derivative of methane, right? You can see if this is your methane, right, CH4, if I replace one hydrogen atom with Cl and other hydrogen atom with phenyl, what I get is this compound, right? So this is your chlorophenyl methane, right? I hope this point is clear. Now we'll undergo preparation of these two types of compounds. The first type of compound, which is your chlorobenzene, is prepared majorly by two ways. First is by direct halogenation of hydrocarbons, and here hydrocarbon would be benzene. So direct halogenation of benzene, right? And the second way we'll prepare it is from benzene disonium chloride, right? So two ways. We'll look into direct halogenation of benzene, right, or we'll prepare it from benzene disonium chloride, right? X stands for any halogen, chlorine, bromine, fluorine, right? You have plus sign here and a triple bond between. This is your benzene disonium chloride. These are salts. We'll see how we'll prepare it from here. Now under direct halogenation, right, okay, let's first talk about this. For when we'll study the preparation of aryl halides from benzene disonium chloride, we will go through some important types of name reactions. First is your Sandmeyer reaction, Sandmeyer's reaction. Second is your Gattermann reaction. Third is your Bals and Scheimann reaction, right? These are important name reactions used for the preparation of aryl halides from benzene disonium chloride, right? And benzyl chloride, or these aryl alkyl halides, like I've written here, chlorophenyl methane, right? These are prepared by direct halogenation. Direct halogenation, right? We'll look into difference between direct halogenation of side chain hydrocarbons and direct halogenation of these hydrocarbons, right? So let's first look into the preparation of your aryl halides by direct halogenation, right? By direct halogenation you can prepare chlorobenzene, bromobenzene, right? And idobenzene cannot be prepared by direct halogenation, because the reaction that would result would be a reversible reaction, right? And we know that reversible reaction, your product the reactants will start forming from products, right? So we would be using an oxidizing agent to prepare your idobenzene, right? And fluorobenzene cannot be prepared by direct halogenation, because the reaction between fluorine and benzene is highly explosive, right? It's because the reaction is very strong, right? It's an explosive reaction, so it cannot be prepared by direct halogenation, right? So let's first look into the preparation of chlorobenzene and bromobenzene by direct halogenation, right? So the equation would be, we would be looking into the mechanism of reaction also, right? So we take benzene, reacts with chlorine right, in presence of halogen carrier, right. This reaction is done in presence of halogen carrier, very important, right. This is done in dark room, no light, right. And a halogen carrier, you can use directly your iron, you can use directly a halogen carrier FeCl3, but mostly what is done is we use iron, right. We use iron fillings, right. Iron reacts with chlorine to form ferric chloride, which is a halogen carrier, right. It forms this compound, right, plus HCl. Similarly, to prepare bromobenzene, you take bromine gas. Here you will use FeBr3 in dark room temperature. What you get is Br, right, plus HBr, right. So these two can be prepared via direct halogenation, right. I hope this is clear. So, right, these are simple reactions, right, and these types of direct halogenation, right, these are termed as, we call these direct halogenation as your nuclear halogenation. Nuclear halogenation, why? Because here we know we have a hydrogen atom which is directly attached to the nucleus, right. So hydrogen atom which is directly attached to the benzene nucleus would be replaced by chlorine here, which is your electrophile, right. This is your electrophilic substitution reaction, right. So here chlorine, this chloronium, right, we'll see how chloronium is generated here. Chloronium will replace hydrogen atom of the benzene nucleus to form chlorobenzene, right. Same as with this bromobenzene, where bromonium will replace hydrogen atom directly attached to benzene nucleus to form bromobenzene. This is your nuclear halogenation, very important, because here halogenation or the halogen atom is directly attached to the benzene ring, or halogen or this your bromobenzene or chlorobenzene is formed by replacing hydrogen atom of benzene nucleus by chlorine atom, right. And second important thing about this is this proceeds via electrophilic substitution reaction, right. We have done electrophilic substitution reaction in mechanism of organic reactions. Electrophilic substitution reactions, right. Why? What are electrophilic substitution reaction? Where a weak electrophile is replaced by strong electrophile, right. It is replaced by strong electrophile, right. Here the weak electrophile is your hydrogen, right, proton, and your strong electrophile is your chloronium, right, in this case bromonium. So this electrophile will replace weak electrophile proton, right. Now coming on to the other reaction to prepare iodobenzene, here reaction is done in presence of an oxidizing agent, but first let's see. An iodobenzene will get formed, right, plus hydrogen iodide, right. This is a reversible reaction, right. When we say reversible reaction, here these products will react to give you back the reactants, right. So in order to prevent the reversibility of this reaction, we will use an oxidizing agent, iodic acid, right, HiO3, iodic acid. Iodic acid will react with hydrogen iodide to give iodine gas, right, iodine gas and your water, right. This is important to understand in this reaction. right? So iodic acid will react with hydrogen iodide, right, to give you iodine gas, right? So this is how this will not react with your iodobenzene to give you benzene and iodine back, right? This is how the reversibility of this reaction is prevented, right? I hope this is clear, right? So it will react to form water also, right? This is important. Just remember about this reaction that this is a reversible reaction in the absence of iodic acid. So to prevent this reversible reaction, what we will do is we will use an oxidizing agent, which in this case is iodic acid, HiO3, which will react with hydrogen iodide, because it is due to this hydrogen iodide the reaction is reversible. So it will react this with this hydrogen iodide and will form iodine and water, right? So this is how reversibility of this reaction is prevented, right? The other reaction is to prepare fluorobenzene, right? Now fluorobenzene cannot be prepared by direct halogenation because the reaction between benzene and fluorine is explosive. So no reaction between fluorobenzene, no reaction to make fluorobenzene from benzene and fluorine, right? Now let's look into the mechanism of this reaction. Mechanism. First, like I said here, this is an electrophilic substitution reaction where a weak electrophile is replaced by a strong electrophile, right? So here weak electrophile would be your hydrogen or a proton, right? Or a proton, this which is attached to the benzene nucleus, and your strong electrophile would be your this Cl plus chloronium ion, right? If you are preparing bromobenzene, it is bromonium ion. So let's see how this is generated in mechanism. We will see how chloronium ion is or bromonium ion is generated, which is an electrophile, and what is the role of ferric bromide or ferric chloride, right? This ferric chloride and ferric bromide, these are basically called as halogen carrier, right? So ferric bromide or ferric chloride that we use here, these are your FeCl3 or FeBr3, these are your halogen carrier. These are your halogen carrier. Now let's see what do they do in order to produce an electrophile, which is your chloronium or bromonium, right? Just look at this. We have chlorine here, right? And we have ferric chloride, right? So this ferric chloride, right, which is a halogen carrier, will attack this chlorine to produce chloronium ion. That chloronium ion will then attack the benzene nucleus, right, to form a carbocation, right? So first this ferric chloride will cleave this chlorine molecule to give you FeCl4, which is a base, right, plus your chloronium ion, right? Now this chloronium ion will attack, right, your benzene nucleus to form a carbocation, right? Because in mechanism what we basically do is, what is a substrate, right? What is a substrate here is benzene, and what is a reagent? Reagent is something that produces or something that creates electrophile or a nucleophile. We know a positive and negative reagent, right? So here reagent we have is ferric chloride, right, which produces this positive reagent, which is your electrophile chloronium ion, right? So it will attack your benzene nucleus, right, to form a carbocation. We know that carbocation is an intermediate, right? Carbocation is a intermediate and is, we'll just understand some important thing about these, right? Since this is a intermediate, this is resonance stabilized, right? This is resonance stabilized, right? I'm just drawing different resonance forms. Then the other you have is hydrogen and chlorine, right? These are resonance forms, right? And this is a carbocation, a sigma complex. We will call it a sigma complex, right? Let's draw the resonance hybrid. It will look like this. Right, this is your sigma complex. Now what is a sigma complex? Why do we call it this is a sigma complex? Why do we call it a sigma complex? We call it a sigma complex because chlorine is attached to this benzene nucleus via sigma bond, so we call it a sigma complex, right? And the other important thing about this reaction is that this benzene, just understand, this benzene is stable. Why it is stable? Because of its aromatic character, right? This is, here you have the benzene is aromatic, right? This carbocation is not aromatic, right? So this is unstable, this is stable, right? Now since this is a carbocation also, which is, again, we know they are reactive species, right, which are unstable, right, because they react whatever they found around and to form products, right, to gain stability soon. So this is a carbocation. This carbocation, remember, is non-aromatic, right? And this is your aromatic system. We know that non-aromatic system is unstable, right? And everything tries to attain stability. So it will soon change into aromatic system. And how it will do that? It will lose a proton to this base that was formed here. Right? Let's write it like this. This sigma complex will lose hydrogen ion, right? Lose hydrogen ion to form your chlorobenzene. This is how it gets formed. Now again, you can see this is non-aromatic and this is your aromatic. Let's write it like this only. This is how sigma complex is. So sigma complex will lose this hydrogen atom to this base, right? And this is your, again, aromatic, right, which is stable. So it has gained stability by regaining its aromaticity. Aromaticity is regained in this electrophilic substitution reaction. And like I said, this proton will react with it to form FeCl3, right? This is the mechanism of this reaction, right? And I hope this is clear, right? Just remember that this is lost, right, where it will react back with this base, right, to form HCl and ferric chloride, right? And remember, this is an electrophilic substitution reaction, right? Now if further substitution is done, right, or what we say is, just remember this, that we have taken, in these two types of reaction, we have taken benzene, right? We did direct chlorination of benzene. right? In direct chlorination of benzene, a chloronium electrophile is generated, right, from the ferric chloride. Ferric chloride is a halogen carrier. It is a halogen carrier. The work of halogen carrier is it carries electrophile, this chloronium, it generates this chloronium which gets to the benzene ring, right? So that is why it's a halogen carrier. So it will cleave this chlorine to give you this base and chloronium ion. This chloronium ion will attack benzene nucleus, right, and it will form this carbocation. We know carbocation is an intermediate which is unstable, right? And you can also see that it has lost its aromaticity, right? This is non-aromatic, which is less stable system, so it will try to gain stability, and this is your sigma complex. Chloronium will attack benzene nucleus to form this sigma complex. Why we call it a sigma complex? Because chlorine is attached to benzene nucleus via sigma bond. So it will lose proton, right, to this base to form the product chlorobenzene. This is its mechanism, right? And your HCl and ferric chloride is formed, right? I hope this is clear. Same goes with bromine, right? Now if further reaction is carried out, if chlorine is taken in excess, same reaction, if chlorine is taken in excess, this chlorine is in excess, then products that are obtained here would be this and this. This is important to understand, right? This is your ortho isomer, right? Because here chlorine, the second chlorine atom that has entered this benzene nucleus has occupied this position. This position is your ortho position, and this has occupied this position. This position is your para position. So this is your para isomer, right? And why it has entered ortho and para position. This is ortho, this is ortho, this is para. Why it has not entered this meta position? This is your meta positions, right? The reason is because we know that there is something known as directive influence, right? Directive influence of these substituents attached to benzene nucleus. When further halogenation is done, right? Further halogenation is done, the second chlorine atom that will join this benzene ring, right? The entry or the position of second chlorine atom would be decided by the already present chlorine atom, right? And this already present chlorine atom decides the orientation of the incoming group, right? And this is ortho and para directing. It will direct the second chlorine atom at ortho position and para position, right? And how it does that, I'll just give you a little introduction. We have done this in electrophilic substitution of aryl halides in detail. This chlorine has lone pair of electrons. These lone pair of electrons will enter into conjugation with the benzene ring, and it will produce sites of high electron density at ortho and para position, right? So at ortho and para position you have high electron density sites, and we know that in this reaction the electrophile is chloronium ion, right? Chloronium ion. So chloronium ion, which is an electrophile, we know that electrophile will always attack at sites of high electron density, right? So these are sites of high electron density. So either chloronium ion will attack at ortho position to form ortho isomer, or it will attack at para position to form para isomer. That is why you get ortho and para product, right? I hope this is clear, right? So these are your ortho and para product, and we now are clear why do we get ortho and para product, right? Because your benzene is ortho and para directing, right? What you need to remember here is that one thing that you might have done in hydrocarbons chapter, the directive influence of substituents, right? For example, you have chloronium here. chlorine atom. Chlorine is chlorine, bromine. These are ortho and para directing groups, and I have explained you how these are ortho and para directing group. If you have nitro here, right, with this nitro is a meta directing group, right? So if you have nitro here, suppose, so nitro group will direct the incoming group at meta position, at this position, right? So these are ortho para meta directing influence of already present group, right? So important thing to remember is why do you get here ortho and para isomer is that the entry of the second chlorine atom would be decided by the already present group, which is known as directive influence of the substituent, right? And so that is, since your already present group is ortho and para directing, so the second chlorine atom would be attached to the ortho and para position of the benzene ring. And why it is ortho and para directing? Because your lone pair will enter into conjugation with the benzene ring, creating sites of high electron density at ortho and para positions. And since this is an electrophilic substitution reaction, so electrophile chloronium will attack at ortho and para positions, right? I hope this is clear. Now let's quickly look into your side chain substitution, preparation of aryl alkyl halides, these types of compounds, right? We'll look into this quickly, right? So here we'll again go for direct halogenation to prepare alkyl aryl halides. Here the substitution will not take place at benzene nucleus directly, but will take place at side chain, right? So suppose you need to prepare this compound, benzyl chloride, right? What you will do is you will take this compound, toluene, right? This is the side chain, right? So substitution will occur here at the side chain, CH2Cl. This is known as side chain halogenation. This was nuclear halogenation, right? These reactions are nuclear halogenations. I have mentioned here nuclear halogenation, and this is your side chain halogenation. Side chain halogenation, right? And this is the conditions for these reaction is these reactions are done in the presence of sunlight, 383 Kelvin, right? And you have no halogen carrier. For side chain halogenation, you need not any halogen carrier, no halogen carrier, right? And the mechanism of this side chain halogenation is your free radical mechanism. Like this was electrophilic substitution reaction, so this is free radical reaction. This will proceed via free radical reaction mechanism, like normal hydrocarbons does. Like chlorination of methane, it goes through free radical mechanism, right? So this also proceeds via free radical mechanism, right? No halogen carrier is required, because halogen carrier was required here to produce electrophile, right? Because this is an electrophilic substitution reaction. Now this is a free radical substitution reaction, where in the presence of sunlight, free radicals this chlorine will form free radicals, right? It will form free radicals, and this free radical will then attack this benzene ring, and it will proceed via free radical substitution reactions, right? I hope this is clear. Now after this we'll just look quickly into, in the second lecture we'll just quickly look into the preparation of aryl halides from benzene diazonium chloride. Thanks.